Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. And we're doing a toughie today, okay? Alien Dictionary 269. It's an old one and Facebook and Amazon are still asking it a lot. I'm not even going to begin to admit how many hours I spent trying to wrap my head around this one. So it's 5 p.m. here right now, and I've been on this pretty much all day. But I think I finally got a hold of it in a way where I can explain it to you guys in 20 to 30 minutes, hopefully 20. And I hope that it helps because this one is not easy. It's really not easy. So without further ado, let's dive into it. We're told that there is a new alien language which uses the Latin alphabet. However, the order among letters are unknown to us. We receive a list of non-empty words from the dictionary, where words are sorted lexicographically by the rules of this new language. Derive the order of the letters in this language. Okay. So we're given a bunch of words, and they're in some order. Some lexicographically, if we were to use our standard alphabet, would be equivalent to saying alphabetically ordered. The reason it's not quite alphabetically ordered, if you will, is because we don't know what the order of this new language is. In this example over here, we're given five words or five strings consisting of seemingly random characters, and in fact, if the alphabet was WERTF, this would be in their alphabetical order or lexicographically sorted. What we need to do is, given this list of words, we need to spit out the order of their alphabet, the order of the letters in this language. Note that not all of them are possible. This order here, for example, is invalid because we got a Z, followed by an X, and then followed by a Z once again. So it's inconsistent because it would seem that Z comes before X. But then in this next step, it seems that X would come before Z, and that's a logical contradiction. And so once we come across a contradiction like that, we will just return an empty string. We are given a few notes. We're told that we may assume all letters are in lowercase. If the order is invalid, we return an empty string, and there may be multiple valid orders of letters. We can return any one of them. So that last part, I think, is going to be at least somewhat important in understanding how we can come across an answer. And I wanted to walk through maybe a bit of a simpler example to help understand what's going on here. Maybe even before I go into that example, we can look really quickly here at this one again. If we kind of look downwards, so I'm looking down the first column here, we can kind of deduce that W would come before E, which comes before R. And that's fine. As we walk down here, we're not really learning much. Maybe between this word and this word, we can see, okay, well, F seems to come after T. And I don't know if we can, how would we figure out here? We've got ER and then we've got ET. So we can figure out that the T comes after the R. And just by eyeballing it, maybe you'll start coming up with kind of different ways of solving it. And one way that I tried to do was, it was almost like an iterative approach of walking through column by column and deducing what I could, depending on what letter I'm at and how the column kind of above me played out, as well as the words so far, if you will. I tried that approach. I didn't get it completely working. I think it would have definitely timed out even if I didn't. So one of the difficult things to realize about this problem is how to think about it in terms of the relevant data structures. And maybe if we walk through this example, it'll give you a bit of a hint. I'm not going to spoil it just yet. The key here in terms of the insights that we're going to gain is going to be a couple of things. One thing is we need to think about how each word relates to its preceding word. What logic or what did I learn from my preceding word given the word that I'm at right now? And let me walk through this just to be a bit more clear. I'm going to begin by looking at these two words first. I've got ZA and ZB. Comparing these two, I noticed that their first letters are the same, so I don't glean any insights there, nothing new. I look at these two next and okay, well, if I've gotten this far, everything before them was the same. So if I see an A here and then a B, it must be true that in this alphabet, A comes before B. Okay, A comes before B. That must be true from what I've gained here. Fine. Let me take one more step down. Let me see what I can learn from these two. I'm now going to look at these two consecutive words. I've got ZB or ZB and then CA. Well, we can tell here their first letters are not the same. We've got a Z and then we've got a C. What that means is that Z must logically come before C. Okay, I think that makes sense. Again, I'm not even going into the algorithm or any programming yet, just kind of looking at this step by step. Finally, I'm going to look at these two words in combination. The first letters are the same. We don't get any new insights there. I look at the next two and I see A comes before B. It looks like we kind of knew this though, so maybe this won't really help us very much. But regardless, really there's two pieces of information here. I know that A comes before B in this alphabet, and I know that Z comes, I'll stick with the Canadian pronunciation. Z comes before C, just because Z and C are similar. A before B, Z before C. So what does that mean? Maybe the alphabet looks like A, B, Z, C. Maybe it looks like Z, C, A, B, right? These are the only two conditions I have. So as long as my answer is consistent with those, I'm good. Maybe it's something like A, Z, B, C. Oops, C, right? A comes before B, Z comes before C. Or even something like A, C, B, Z. Did I do this one already? I want to make sure I didn't make something silly. Anyways, the truth is, again, A comes before B. This one doesn't work. C came before Z. Anyways, I'll kind of cut it off here. I think there are a couple more options, but each of these is valid in their own way, and there doesn't necessarily need to be one right answer. We don't need to produce all the answers, but we need to give one of the answers. So how do we do this? Well, if maybe I give you a bit of a hint by the way that I kind of drew these out. And one of the first big insights you need to have in order to get to the bottom of this question is to understand that each letter, each character within this alphabet, and at most there can be 26 of them because this alien language uses our alphabet, or our letters, excuse me. What if we thought of each one of them as a node? And what if we could draw a graph out and say maybe we have a node that A and then that one goes to B. And it's not necessarily directed, okay? It's not necessarily directed, but we've got a graph that looks something like this. In fact, it's not even a fully connected graph, is it? Right? Because I don't have any connection between the Z and the A or the B and the C, but that's fine. You know, we're actually okay with that here. Where you'd get an issue or contradiction is what if we had a cycle anywhere? So what if the Z pointed to the C, but the C also pointed to the Z? So that was like the example we looked at where we had a Z, X, and Z. From here, we would have learned that Z comes before X, but then here we would have learned that X comes before Z, and you'd have this cyclic structure. And that's no good. So one piece to understand here, and I don't know, maybe it's intuitive for you guys, but it definitely wasn't intuitive to me to think that the alien dictionary problem is fundamentally a graph problem. Okay, so that's one thing we can gain here. So to get typically when we do a graph problem, that'll involve actually creating some sort of graph, meaning that we want to come up with some way to build an adjacency list. And I think that's good. So we start with one node in our adjacency list. We'd have something like, we keep it in a dictionary, and we say A points to B. Maybe I'll keep all these in like a set structure. This looks like a tuple, but it's a set. Z goes to C, and in this case, it's a pretty simple graph. Something to think about there. Sorry, my hair and hat, everything's all over the place. Oh boy, I'm in a communist era hand-me-down sweater. Not looking hot today, not looking hot at all. We build an adjacency list that looks something like this. And so, okay, that'll get us part of the way. So now we have a graph. We can kind of picture what this graph is like. The question becomes, though, even if we have this graph right now, how do I know just by having an adjacency list which letter will come first? So what is it that separates the A and the Z from the B and the C, right? How do I know that the A and the Z must, in some shape, come before the B and the C? Well, the answer to that question, I'm going to clear this up a bit, so actually, you know what? I can leave it. I can always scroll down. The answer to that is going to be a method of solving graph problems known as topological sorting. And so, strictly speaking, there's a whole bunch of methodology to do this, and you can kind of Google it. I'm not doing a full video on it right now because, quite frankly, I don't think we're going to warrant it when there's only one concept that we actually need to apply in order to get this problem to work the way we want it to. And that concept is going to be the idea of in degrees. In degrees. So if this is your first time hearing about these, hang on tight because it might not be obvious the first time around. We're going to think about in degrees as the following. In degrees, by definition, are the number of incoming directions or edges, the number of incoming edges for any given node. If I was to think about in degrees for these nodes here, this A has 0 edges incoming, okay, 0. So it's got an in degree of 0. Same thing with the Z. However, B has got an in degree of 1 because the A goes into the B. C has an in degree of 1 because the Z goes into the C. If, for instance, the C was going into the B, for example, then B would have an in degree of 2. So the total number of incoming edges that you have coming in toward you, that's going to be your in degree. Now, why does the in degree matter? The in degree matters because by definition of how these work, then the letters that we want to pick first are the ones with 0 in degrees. They are contenders to be at the beginning of our alphabet. A can be at the beginning of our alphabet, and Z can also be at the beginning of our alphabet. B cannot. If B was at the beginning of our alphabet, that would mean that there is a letter out there, namely A in this case, that should be preceding B because we go from A into B. We learned that by doing this analysis over here. We learned that we need to go from A to B and from Z to C. Okay? That is why A and Z are contenders to be at the beginning of this alphabet. B and C could not be. If I put C at the beginning of my alphabet, I can't save myself here anymore, right? If I put a Z anywhere, no matter where I put the A or the B, if I had a Z afterwards, that would be false. It would not be a correct alphabet. We would be breaking a logical rule, which we found here was that Z needed to go before C. So, with all that said, there are two things we're now concerned with. One is we need to build an adjacency list. The second thing that we need to build is we need to build some sort of list of in degrees. Okay, and these in degrees are going to be just a collection of how many incoming edges we have from one node to another. Okay, the way we can build this, and so you can build an in degree using a dictionary as well, where we had maybe one entry for every letter, and each of those letters would contain a count of in degrees. For me, the way that I found it a bit more logical maybe to build would just be to create an array. Since we're dealing with the alphabet, I like to create an array with 26 entries, where the first entry is for A, second is for B, third is for C, all the way until Z. Again, either of these will work. You can play around the code and make it your own when you're doing your implementation. But in this case, I'm going to stick to doing an adjacency list with the dictionary, and my in degree is going to be built with an array with 26 entries. Now, we've got the adjacency list, we've got the in degrees, which we're going to build, and we'll kind of do these together in one step. After that, it comes down to doing a walkthrough of the actual graph. And I think in this case, what we're going to do is we're going to do a breadth first search. And from there, I think once we get to that point, we'll basically say, okay, we've got our adjacency list, and knowing these in degrees, kind of every time I visit one of these nodes, if it's got if it's got some in degree, we're going to reduce it and say, okay, I've visited it from one spot, and if eventually it gets to having an in degree of 0, we're like, okay, this is now a contender to be next in my line of alphabet, alphabetic letters. If I started, for instance, with building my dictionary where I said, okay, we got an A, and from the A and Z, and let's say on our first walk, we realize A and Z are the only entries with 0 in degrees. Again, this could have been just as easily, this could have been ZA, it doesn't matter. For illustrative purposes, I'm just going to go with AZ. Once I visit the A, I'm going to check all my neighbors of A. Well, A goes to B. B has got an in degree of 1. If I go from A to B, we've imagined almost removing an in degree of B. If I remove that in degree, it's going to go from 1 to 0. If it goes from 1 to 0, I go, okay, now we have an option for B to be the next contender of letters coming in. So then I add it to my queue, and eventually we'll pop it into the result. When I'm visiting all the neighbors of Z, I'm going to notice that C is one of the neighbors, and the in degree of 1 will become an in degree of 0 because we've visited it, if you will. And then C is going to be a contender. That's how we get A, Z, B, C. Again, the order of these two can be reversed. And maybe they might be even a bit jumbled up. But as long as A comes before B and Z comes before C, we're good. We're in the clear. And that's going to be the general logic behind how we're going to build this. I hope that explanation made sense. I tried to make it as simple as possible. Again, I've spent it must have been 8 hours on and off trying to wrap my head around this and piece it all together. So I hope this was cohesive enough and not too short. If you have any questions about anything I've said so far, drop it in the comments down below, and I'm happy to address it. Right now, though, let's take a stab at the code, which will, in and of itself, require a bit of a heavy lifting. So a couple of items that we needed to take care of were the following. We said we need to build adjacency list. And by the way, we were told that we're actually given a list of non-empty words here, so the input's going to be legit. That's why I'm not doing the error checking this time. So we're going to build an adjacency list and in degree list. Okay. After we build those, we're going to do our BFS, and then we're going to return our results. So this is almost deceptive because there's going to be quite a bit of code that goes in, especially here, and then a few slide tricks in the BFS. But generally, directionally, this is what we're going to be doing. So the adjacency list I'm going to build as a dictionary. The in degrees I'm going to call in degree, and like I said, I'm going to do a list, and I'll set them all to 0 for now. So I'll say 0 for some variable in the range of 26. We're going to have one of these for every character. Now, I'm going to begin by populating my adjacency list, where we're going to have for every character that's within any of these letters, I'm going to put in the adjacency list so we can just add into it easily. Again, but for the first time, there are ways to maybe do this a bit quicker with using default dict or even ordered dict perhaps, but I'm just going to run with first principles like I usually do. So I'm going to say for word in words, and then for every character, so for every C in every word, I'm going to say that if the character is not in the adjacency list, then I'm going to add it into the adjacency list. So we'll say adjacency list of C is equal to a new blank set. That's going to take care of just building the adjacency list itself. The next piece now is going to be adding these edges in and filling in the in degrees. And so this is why I'm going to do this one in a separate for loop. What I'm going to start with doing here is this piece of logic right over here. We said let's figure out how we're going to get these edges by actually determining the comparison of two words at a time, sequentially jumping down. So looking at these two, then at these two, then at these two, all the while checking the first column of letters, followed by the second column, followed by the third column, and so on until we see a difference in letters. Once we see that difference, we know that, here we saw no difference. Okay, so we moved over. Then we saw a difference here. So we determined that we must be going from A to B this way. And that's how I'm going to actually build what my edges are going to be. So I'll say let's say for I in the range of 1 until the length of words. So the reason I'm doing this is because I'm going to have two words that I'm comparing. One word is going to be my first word, so I'll call it first, and that is going to equal words of I minus 1. The second word is going to equal words of I. So imagine we're starting at 1, then words of 1 is going to be your second word, words of 0 is going to be our first word. So this would be our first word, this would be our second word, all right? I'm now going to need to iterate through both of these letter by letter. The amount that I'm going to have to iterate through by is going to be whatever the minimum length is of the two. In this case, we were kind of spoiled because I chose an example where they're the same length. But if one of these is length 2 and the other is length 5, we're going to run out of bounds if we go, past the length of the shorter one. So what I'll do is I'll get a variable here called length, and I feel like I'm going to run out of space here eventually. I'm going to move this over. Length is going to equal the minimum of the length of the first and the length of the second. Now we're going to have to jump into this for loop of comparing the character by character, almost columns if you will, for these words. So I'll say for j in range length, and then this is where we are going to start looping through these. I'm going to be interested in comparing the two letters only if the following happens. If the actual letter, so if first of j is not equal to second of j, then we're going to do some cool logic. So what that basically means is that if they are equal, like z and z here, I don't want to do anything. I don't care. Just take me along to the next j. So we could, if we wanted to do something like if first of j equals second of j, equal to second of j, then continue. But I don't really see a point in doing that here. So I'm going to do it here. So we're going to do some sort of logic here, and then what I'm going to do is I'm going to say once I've found my first mismatching characters, after I do my logic, I'm going to break out of this, so I'm done with this for loop, okay? And I'll fill in the logic here in a second, but I do want to show you guys one trick that is going to come in handy, and this is something that I just learned today. I was today 8 years old when I learned about this, and I wanted to share with you guys because it works really well for this problem. Let's say that I walk through these and maybe I've got two identical words. Maybe I had ZA, and right before it I had a ZA as well. Okay, so technically a valid entry. I'm not really sure why you'd have duplicates, but hypothetically, let's say this happened. In that case, I would never break out of this. So I would walk through this entire loop, but I never would have hit this break statement, which means I haven't done anything. All the letters were the same. Everything I've compared has been identical. In that case, if I never hit the break statement, I can actually do a for else statement. And what the for else statement is that you only enter this else if you did not break out of this for loop. Why this works is because if I'm walking through a for loop and then I want to say at any given point, okay, like I found the thing I'm looking for, break and exit out, then I'm not going to hit this statement. I'll say mission accomplished. If I didn't do that and mission was not accomplished, then I might want to say, okay, is there something else that I need to take care of here because I didn't find what I need? The answer is yes, we do. And the thing we want to find is going to be the following. So we're all good here. If we got ZA, that's valid. The issue is, what if I had something like ZAY? Okay, imagine I had ZAY. Because of our logic where we're only walking through the minimum of the two lengths, this is all I would ever compare. Okay. However, this word is longer than this one. Lexicographically, this is no good. Okay, if this one came before it, so if we had ZA and this was ZAY, that's all right. Right? We don't have an issue here because this is a prefix to this word. However, if that's not the case, then I have an invalid entry. And what that tells me is that, you know, if the length of the first word is greater than the length of the second word, and again, so if we had something like ZAY, so if it's longer, right? So if the length is greater than the second, and I didn't break, meaning, you know, I only compared ZA with ZA, I never broke because I never found mismatching characters, then I've got an issue. So something is invalid. And in that case, I'm going to return an empty string. Okay, and I don't mean to take all the rest of the logic we're doing out on a tangent, but this is a small piece of code that will actually change our final answer and will help us get through those final few edge cases. So that's why I'm building this into here. Now, for the actual logic on what we're going to put in here, we kind of said that we're going to be looking at, if we find mismatching characters, we have an edge going from the first to the second, okay? So if I'm going from the first to the second, I'll say that maybe character out, so imagine like an out degree versus an in degree. I'm going to have character in, a character out, and character in. Character out is going to equal first of J, and character in is going to equal second of J. And I'm only giving them their own variables here. You don't need to, but I just want things to be a bit more legible. If we haven't already determined that this edge exists, so in this case, see, we had A to B, and then we said A to B again, so we saw it twice. Well, we don't want to double tap our logic. So what I'm going to say is if character in is not in the adjacency list at character out. So in this case, we haven't seen that A goes to B. We don't know that yet. We don't know that A goes to B. Then jump in here and do the following and say adjacency list at char in, and remember that's a set, right? It's a set. So I'm going to say dot add character out. That's one of the edges. So A goes from B. We're going from our character in, the first one, to character out. As well, that means that character out has an in degree. It has an additional in degree now. So we've added an additional in degree, and that means that we're going to go into our in degree array and look at in degree of some index, and we'll determine what that index is and add 1 to it. Now, what is the in degree of this index? Well, here I want my character A to go to 0, my character B to go to 1, my character C to go to index 2, and so on and so forth. So what I'm going to do is I'm going to take the ord of my character, and this is a built-in Python function, which will give us I think it's the ASCII code. So if we get the ord of our character in that has an in degree coming in, and did I make this wrong? Sorry, I did this wrong. Character out dot add character in, because we're going from out to in. I'm sorry about that. In degree ord of character in minus ord of A. And the reason we're doing it this way is because if this character was an A, then A minus A would give us 0, so we'd end up in the first index. B minus A would give us kind of whatever the ASCII code is for B minus the ASCII code for A, and that would give us 1, and so on and so forth. So that's how I'm calculating my indegrees here. So this piece of logic and this build right over here is the first step in solving this problem. So what we've done is we built the adjacency list and the integree list. Okay, this is going to be the first chunk. Now the next chunk that we're going to go into is like I said, this slightly maybe modified breadth first search. So for the breadth first search, we're going to begin by creating our result, which is going to be some string. And as always, we want to build a queue. Now, how are we actually going to build this queue? Sorry, this is going to be we'll use the deck. And within this queue, I want to build it, like we said at the beginning, we want to build it for every single character. We want to start with adding every single character that has an in-degree of 0. In this example here, those were A and Z, or Z and A in any order, really. So that's why we're not worried about the fact that we added this to a dictionary, even though the hash might actually jumble around the order. If you didn't want to preserve order, you can use an ordered dictionary in Python, but we really didn't need to here. So what we're interested in is adding characters C for C in adjacency list if in degree of this character is equal to 0. So if in degree of, and now we're going to do the whole ord C minus ord A. Oops, I got to move myself out of the way. Minus ord A is equal to 0. So again, oops. So the logic we're doing here again is just to say every character in the adjacency list, which happens to be all the characters in all these words. We built that at the start right here. If any of them has an in-degree of 0, add it to the queue. Now, while there exists some sort of queue, we actually need to start, popping items off and adding them to a result sequentially. So we're going to say the following: the character C is going to equal Q, and we're gonna pop from the left of the queue. Okay, we'll call this character C, and we'll say result plus equals C. So we're adding it to our results, and we're building our dictionary right here. From this result C now, we're going to say that from C we can go to potentially one letter or multiple different letters. In this case, we could only go from A to B, but maybe here we could have gone from Z to B as well if the words were different. So I'm going to say, I'm going to check all the neighbors of this character C. So I'll say for neighbor in adjacency list of C, we want to do the following. We want to take the in-degree of this index, which we're going to take, and we're going to reduce it by 1. And the in-degree, again, we're going to take the ord of the neighbor, minus ord of A, and that'll give us the index where we're at, and we're going to reduce it by 1. We're then going to say if the in-degree of this item, now that we've reduced by 1, if the in-degree is equal to 0, then we are going to want to append it to our queue. So we're going to say q.append neighbor. Oops, neighbor. And what that's going to do is that if I've gone, for example, from A to B, so this is now going to be down to 0, I'm going to add the B. When I check the C and I check when I check the Z and I check Z's neighbors and I reduce this, the C goes to 0, I'm also going to add that to the queue. I'm going to keep adding these onto the queue so long as they go down to an in-degree of 0. Because like I mentioned earlier, if your in-degree hits 0, you are now a potential candidate to become the next letter in the alphabet. Now, will all the letters make it there? Will they all end up with an in-degree of 0? The answer is not necessarily. Okay, so we're going to have to take that into account when we're returning our result. So we're going to return our result if the length of the result is actually equal to the length of the adjacency list. In the adjacency list, we added every single character that exists in any one of these words. So here, there are 5 different characters. There are W, E, R, T, and F in this example. If I spit out, and that's by collecting literally every single letter here, adding it to the dictionary. If I was to spit out a result that had fewer characters than that, then I have not created an entire dictionary that consists of all these characters. So in that case, I would have to return an empty string. since if I do create one, I've gotten this far and I've created a result that's equal to the length that we want it to be, I will return whatever it is that we put together. And I'm going to run this now. Miraculously, no errors. I actually can't believe it. And there we go. All right, wicked. So I'll show you all the code in a minute, just so you see. I've spammed submit on this code a few times. With this exact piece of code, you'll fall anywhere from like 24 to 36 milliseconds. That'll take you from the 99th to the 50th or so percentile. So this method is legit. Don't let this 54% fool you. And just as a quick recap on what we did, although I'm not sure a quick recap is sufficient, we started by noticing that we need to compare these words 2 at a time. And if we compare them 2 at a time, we can logically put together what relative order we need of some letters. Even if we don't see all of them together just yet, at least from an A to B and a Z to C, we can put that together. If we notice that that's the case, we can kind of put 2 and 2 together and get to the point where, okay, well, maybe there's a way to solve this problem using graphs. And if we got graphs, then I really need to take into account the fact that I need an adjacency list of sorts. So we can build that. That's not really too hard. We build an adjacency list, but then the issue is, where do we start? How do I know if I should start at the A, the Z, or the B, or the C? That kind of introduced the topic of a topological sort, or at least it grazed the subject a bit. Again, this was by no means like a strict topological sort related video. But the one piece of information that we did need to know was this concept of in degrees. And we noticed that, well, all the potential starting letters have in degrees of 0. And if I start at those letters, I can start appending them into my result. And as I check off all their neighbors one by one, they're losing. Every neighbor is losing 1 in degree. And if you eventually get to a letter that now has an in degree of 0, that's a candidate to be next, because everything that should have preceded it has preceded it. Okay, everything that should have preceded it has preceded it. Now there's nothing left to precede it, so it's that letter's time to shine. And that's what we did here with this PFS. So I'm trying to fit the code all in on one screen for you guys. Maybe if I delete a few of these, and voila, we just about got it. I hope you guys found that video helpful. I don't know how long that's been. This is going to be a long one, but like I said, this is I think it's a meaty problem. I struggled with it a lot. So I hope this video helps you guys get it at least a bit. Let me know if you have any comments down below. Like a share, whatever would be awesome with this one. I'm sweating. I'm actually exhausted from even just talking about this one. So if you guys found it helpful, do let me know. Oops. And I will see you guys next time. Peace.